Here we're given a polynomial function and we want to determine the long-run behavior and the vertical and horizontal intercepts. So thinking about the long-run behavior, to determine that we need to know two pieces of information. We need to know the leading coefficient, and we also need to know the degree. The degree would be the largest exponent if this was an expanded form. So without actually multiplying all of these factors together, we can think about what that leading term would be that would give us this information. As you're looking at the function, if you were to multiply this out, if you were going to multiply x minus 3 times x plus 4, we would need to FOIL, and we'd end up with an x times x. We'd have an x squared, and then some x terms, and then a constant. And then if you took that x squared times a factor of x minus 1, the x squared times x would give you an x cubed. And really, since this is an x minus 1 squared, we have another factor of x minus 1. So if you took an x cubed times an x, you'd end up with an x to the 4th power. And then we see the negative 2 out in front. So if we were to multiply this all out, we'd end up with a negative 2x to the 4th as the leading term, and then we'd have additional terms after that. But for us, that leading term is all that really makes a difference when determining the long-run behavior. So the leading coefficient is that negative 2. The degree is the exponent, which is the 4. So as we're looking at these key values, the thing that matters is that our leading coefficient, negative 2, is a negative number, and that our degree 4 is an even degree. So if we're thinking about kind of a well-known function that has an even degree, we can think about what we know about our quadratic, our x squared function, that it's that U-shaped graph that either opens up if the leading coefficient is positive or down if the leading coefficient is negative. So having an even degree but a negative leading coefficient is going to give us a graph where both tails are facing downward. The way that we can write this using our notation for long-run behavior is to describe what happens as x goes to negative infinity. So this is saying as you move to the far left side of the graph, what are the outputs of the function doing? That the outputs, we can describe that as f of x, are going down. So we could say they're going to negative infinity. So think of this as saying as you move far to the left, the graph is going down. As x goes to infinity, so this would be talking about the right side of the graph, the function is also going down, so we would say negative infinity. So as you move to the left, the function outputs go down. As you move to the right, the function outputs go down. So this is what we call our long-run behavior. Now we can begin to think about intercepts. So just like we've done for other types of functions, when we want to find a vertical intercept, this is where we want to evaluate our function. So we're going to evaluate our function for an input value of x equals 0. So everywhere you see an x, replace it with a 0. So we have negative 2 times 0 minus 3 times 0 plus 4 times 0 minus 1 squared. And then come through and simplify. So we have negative 2 times negative 3 times positive 4 times negative 1 squared. Negative 1 times negative 1 is positive 1. So multiplying, we have positive 6 times 4, 24 times 1 is 24. So we write this as an ordered pair, 0, 24. So this polynomial function has one vertical intercept at the point 0, 24. We find that by evaluating. To find the horizontal intercepts, or also called the x-intercepts, we want to solve f of x equal to 0. So we're going to take this factored form, our negative 2 times x minus 3 times x plus 4 times x minus 1 squared, and set it equal to 0. So when you have a function in factored form, things multiplied together set equal to 0. The left-hand side will be equal to 0 if any one factor is equal to 0. We can skip over the leading coefficient negative 2 since it's just a constant, and then set each of the other factors equal to 0 and solve for x. You only need to write x minus 1 equal to 0 one time, so even though we have two copies of that factor from the exponent, if any one factor equals 0, that will tell us our needed information. So adding 3, we get x equals 3. Subtracting 4, get x equals negative 4, and x equals 1. These three x values are also called the zeros or the roots of the function when we describe just the x value. Here we're interested in the intercept, so we'll use those zeros and write our intercepts. So the point 3, 0, negative 4, 0, and 1, 0. So this graph has 3 places where it will either touch or cross the horizontal x-axis at the points 3, 0, negative 4, 0, and 1, 0. All of this information that we have found you can then verify by graphing this function. So either on your graphing calculator or using a site such as desmos.com, put in the original function in its factored form and make sure that the long run behavior matches up with the sketch that we drew and that you see those key points, your vertical and horizontal intercepts, telling you about the short run behavior of the graph matching up with what we calculated. So to find long run behavior, we need to know the degree, the largest exponent and the leading coefficient of our function. To find a vertical intercept, we evaluate plugging in 0 for x. And to find horizontal intercepts, we solve, setting our function equal to 0 and solving for x.